All right, we're ready to rumble. So ready. Let's see here. I don't think there was any admin to do. We had I posted our final exam day on Moodle. Saw it last day. Wait, we did? Yes, did. And last day, as a way of kind of, or maybe I'll do this. Maybe I will just bump this down and do a tiny bit of review just from last day. Because we'll sort of compound, but on last day. So we did simple interest last day. Simple interest, we developed two formulas. We can calculate the amount of interest I as the principal amount invested times the rate as a decimal times the time that it was invested for in years. And then we had those special cases where, okay, it just has to match the rate, but generally in years. I'm gonna need more room than this, I think. Whee! Okay. So where I, and maybe we'll do the A formula too before we get started here. Then we said what? A is going to represent the accumulated amount, right? So after some amount of time t at some interest rate, right, my principal amount has grown to some accumulated amount A. Now A is going to be P, that principal amount, times 1 plus R times T. Or if you prefer, you could say P plus I, right? That makes more sense, but I think the first formula there that we're gonna be using more is a little bit cleaner. Okay. But it makes sense, right? So if I is the amount of interest that you've earned, you can tack it on to the amount that you initially deposited, and then you'll have the total amount in your account after some amount of time t. So let's define, so where I is the amount of interest. So this is a dollar amount, right? P is the principal investment. Did she use principal? I think so, right? Okay, good. Principal or principal? Nice. I'll probably never forget that now. Principal investment amount. Also a dollar amount. It is principal. Is it? Mm-hmm. I think it's because it's the first. Like your principal, your initial investment. Whereas principal is like, no, my morals say otherwise. Right? The principle of the thing. Principal, just first. Cool. The more you know. The more you know. Etymology, sort of. I love etymology. Study of words. Origin of words. No. Wow. Can't wait. Well, we're done here. I gotta go check out this app. Hey, no judging. Or is the interest rate as a decimal? That's important, right? So it's usually reported as as a percentage. We have to divide it by 100, and then you'll have your R. Okay? And let's add in annual rate. We only saw one example where I kind of flubbed it, and it was a monthly rate, and then we had to change T to match the months. But if we just force them all to be annual, then we're safe. Okay? And then T is the time in years. Oh, good. I've got one more line that I can bump this. Oops. And A is the accumulated amount. But it's also called the future value, which is also a dollar amount. So we use A for the accumulated amount. And I mentioned the future value because she becomes inconsistent, and sometimes she asks for, and she is the author, she asks for the future value sometimes, so then it's good to have that connection between, okay, it's the accumulated amount or kind of the final amount. Okay, so right, in the simple interest problem, right, we deposited some amount of money, P, and let it grow for some amount of time, and then we have some final amount that's slightly higher with interest, right? Whether we deposited that amount and then we get a bigger amount at the end, or if we borrowed some amount and then we have to repay a larger amount at the end, right? It doesn't matter, it behaves the same way. It's just one is more fun to think about than the other, right? And so now, most savings accounts and most kind of bank transactions, so mortgages, car loans, etc., they're usually built on compound interest. Okay, and so compound interest is kind of fun, where you say, okay, I have $100. Let's say I go in and I deposit it in my bank account, and my bank is committed to giving me some interest rate, right? And I'm going to earn money on this money. And so it sits there for a year, let's say, and then I have $110, let's say, right? So $10 in interest I've made, and now after a year I have $110. How compound interest works is then we can start the clock again, but now it's pretending like, okay, now you're going to earn money on $110 instead of just the $100, right? And so every time that you kind of compound the interest onto the principal amount, right, then, and that's going to happen with some frequency, then you're earning interest on a higher amount than you initially invested, right? Slightly more complicated, but it behaves in the same way. And so I kept this little example here. Suppose we deposit $200 into an account that pays 8% interest. At the end of 1 year, we're going to have 200, so your principal investment plus 200 times 0.08, right? Because the time is 1 year, you know? Which puts me at $216. Now, what's going to happen in compound interest is, what if you put this amount, 216, back into the account, right? Let it grow again. Now you're not just starting from 200, you're starting from 216. Okay? So then after another year, we're going to have 216 plus 216 worth of interest times 0.08, which puts us at 233.28. Now, as an exercise, I want us to establish, well, how does that compare to simple interest, right? Just kind of as a review. this 233.28, right? That's the accumulated amount, A, after 2 years at a rate of 8%. And so here we're given P is 200, that's the initial amount. And to save some space here, I'm gonna just write across. The rate, the interest rate was 0.08 because it's 8%. And then in this scenario, T is going to be 2 years, right? Because I want to compare this $233.28 to a simple interest scenario. And so here, A is going to be P times 1 plus R times T. P was 200 times 1 plus 0.08 times 2. Do you think it's going to be higher or lower? Probably lower, because we're earning interest on $16. It's not going to be a huge amount lower, or a huge difference, I should say. But there should be some difference. 0.08 times 2 plus 1 times 200. I get an accumulated amount of 232 even. Oops. Nice. So compound interest works in our favor, especially if we're saving monies, right? And so versus 233.28 for interest, and I'm going to introduce the terminology here, interest compounded annually. That compounded annually is referring to, okay, well, how often did we stop and check in? How much interest have you earned? And then kind of smush that. Compound means smush, right? You can call it smushed interest, right? But how many times or how frequently do you kind of smush your principal amount with your interest and then start making money on your interest, right? And so we're going to talk about compounding periods or compounding frequencies. Okay. And so, but this compounded annually is how frequently we combine interest earned, right, with our principal amount. We combine interest earned with the principal amount. If you're interested in the textbook, she does go through and she develops kind of how we get to this formula. I think that that's sort of confusing. So I'm just going to jump in and give you the formula and then we'll dissect it instead. I think that makes more sense. And so this leads us to, okay, so compounded annually. So how frequently we kind of combine this principal amount to how frequently are we kind of adding the interest that we've earned so that we can earn interest on our interest, right? And so banks often compound interest more than one time a year. Usually it's twice per year, but it depends, and it'll be in that very, very fine print of whatever agreement you sign. But consider a bank that pays 8% interest, but compounds it 4 times a year or quarterly. 4 times per year, right? So that's quarterly. But the curveball that I can think of is how many months are in a quarter? There's 3 months in a quarter, right? That's kind of a weird thing to think about, right? So every 3 months is quarterly. I know, but we'll make a list of all the common compounding frequencies. And so this means that every quarter, the bank will pay an interest equal to 1/4 of 8%. So they don't just give you all the 8%. They say, hey, you're going to get 1/4 of 8%, which is 2% every quarter. Right? So they parcel it out too. So let's do this. Add a page. I feel like I'm constantly adding a page. Let's do this. Some common compounding periods or frequencies. Compounding, I'm going to call them frequencies. Just because the period to me is the length of time, but what we'll be interested in is how often are we compounding? And so I'll call it the compounding frequencies. Annually, 1 time per year, times per year, of course is just 1, semi-annually, twice per year, quarterly, 4 times per year, and maybe I should make Oh, you want to go that hard, huh? Not until next week, but we will do mortgages and things like that. So, yeah. So I'll leave you on that cliffhanger for a bit. But I mean, there's lots of fun mortgage calculators and calculators. Just because I wanted to say monthly, of course, is 12 times per year. There's bi-weekly. I don't think that's going to come up though. It's 26. Nah, weekly. It's 52 and daily. 365. Let me just use those standards. So you'll want to have a good handle on those, but I think there aren't really any curveballs here except potentially semi-annually, because it's 2, but. So if we invest a lump sum amount of P dollars at an interest rate R, compounded N. So that's our newest addition to the family here is a lowercase n, which is going to be the number of compoundings per year. Yeah. So I'll make a note of that down here, but let's just read the rest of this blurb first. Then after T years, and so now T is definitely going to be in years, then the final amount is given by this formula. I'll hold off. And so this part we don't really need, so let me crop top it. Hey, crop there. Okay. So here where, and I'll do it in pink because it's new. N is the number of compoundings per year. That's our only new addition. Right? All the others have the same meaning. A is the accumulated amount or future value. P is the principal amount. R is the rate, but now we're forcing it to be the annual interest rate. And T is the time in years. Okay. Those we know already. Okay. So in this A equals P times 1 plus R over N to the power of N times T, let's talk about what R over N does. R over N is going to take that annual interest rate and divvy it up over however many compoundings, right? You don't get the full amount every compounding, right? And so this R over N divides the annual rate over the N compoundings per year. Okay. What's N times T? N is the number of compoundings per year, and T is the number of years. So that's got to be the total number of compoundings, right? So how many compoundings are you letting this thing sit for? And so here, this is the number of compoundings for the entire term of the investment. Or loan, I guess, but it's more fun to think about investments. And like I said, she does have a nice explanation of how this formula comes about, but I think we can just kind of accept it as fact. And now, right, just like before, there are only so many components, right? We have how many components? N, A, P, R, T. I guess I didn't actually count them. We have 5 components, right? And so as long as I have 4 out of those 5 things, then I can solve for the 5th, right? And so that means that we'll be able to solve for A, we'll be able to solve for P, we can solve for R. We usually don't solve for N, so that's kind of out. But we can solve for T. So usually N is given. But we can use this formula to solve for A, P, R, or T. Only one at a time, of course. Wow, I wish she would give an example of each of those. You got it. I'll give a little bit of space up above here so we can kind of label it what it is that we're solving for, right? But our first example here is if $3,500 is invested at 9% compounded monthly, okay? And remember, on the test and on the final exam, you're gonna have to figure out whether to use your simple interest formula or your compound interest formula, right? And so this compounded monthly is going to be your clue, right? Whereas all the other questions last day said simple interest, right, at a rate of 4% or something, right? And so this will kind of determine which formulas to use. So compounded monthly gives us the frequency. What will the future value be in 4 years? And so that's why I highlighted that the future value is the accumulated value, right? And so just like last day, I think it's really helpful to try to figure out what is it that I'm trying to solve for here. And in this case, I want to solve for A. Okay? And so here, what will the future value be, which is A, in 4 years? And so this question or this example is an example of solving for A, what that would look like. Notice we're given all the other components, right? And so let's list them. I have P, which is the initial amount that I've invested. Right? I have R, 0.09. Making sure you rewrite it as a decimal, right? Not just 9%. I need N, compounded monthly, so N is going to be 12. This doesn't look like an N. And maybe in our list earlier, we can go back because we talked about these compounding frequencies, but these are really going to be N's. Now that we know what that is. So if it's compounding monthly, that means at the end of each month, you get to calculate, or the bank calculates how much interest you've earned that month and then tax it on. And then for the next month, you earn money on not just your initial amount, but also the amount of interest that you've earned, and so on and so forth. So N is 12 and T is 4 years. All right. It's a compound interest problem, and so that's going to tell me which formula to use. Right? And so here, for compound interest, I use A as P times 1 plus R over N to the power of N times T. Make sure that you simplify your R over N before you add it to 1, right? You have to do your division before you can do your addition, and also simplify N times T. It just makes it a little bit cleaner. So now A is, now it's just a plug and chug issue. 3,500 times 1 plus 0.09 divided by 12 to the power of 12 times 4. .09 divided by 12. It's very small. Plus 1. I'll write out some steps here. 1.0075 to the power 12 times 4 is 48. So 3,500. Oops, sorry. I need to do 1.0075 to the power of 48 first. Times 1.43140533. I'm mostly writing out these steps so that you can check your work on your calculator as you go, just to make sure that you're doing it right. But you don't have to show these middle steps if you don't want to. Times 3,500. 5,009.918667. How can I gain just one tiny line? Can I? That's weird. Whee, even weirder. Smush it up. A is a dollar amount, bless you. 5,009 and 92 pennies. That seems like a lot. Generous interest rate. Let me just make sure I did it right. 0.09 divided by 12 plus 1 to the power of 48. Can't believe my eyes. I did. How much interest did you earn? That's what I was reacting to. You earned a ton of interest. The difference here, right, between A and P, that's the amount of interest that you've earned. You didn't do anything. You didn't add any monies or anything like that, right? And so in only 4 years, right? So the amount of interest is A minus P, 5,992 minus 3,500. So the amount of interest that you made is 1,509.92. Very exciting if you've put it into a savings account, and kind of a downer if you borrowed 3,500 and now you have to repay 5,009.92. They work the same. But that's such a bummer. Nice. Questions about that one? No. Okay. Let me move these guys down. Solving for, well, we have to read it first. How much should be invested? Okay, sounds like P to me. In an account paying 9% compounded daily for it to accumulate to $5,000 in 5 years. I'll let you try it. I'll write it out in silence, or try to be silent about it. But we are solving for P here. Did you get the same thing?
Yes.
Nice. That's fair. Yeah, you want to start here and then go here, but it helps if you've already calculated this one. That was my flub. I had to ditch this number. I could have stored it to calculate this one. What a mess. But you'd need to invest 3,188 and 32 pennies. And like before, I want to see the full number. Hey, where's my pointer? There. I want to see the full number. And then for money, you can round it to 2 decimal places. Right? Money is 2 decimal places, but the answer is more. Nice. Okay, so we've solved for A, we've solved for P. What does it look like solving for? Well, we'll see if it's R or T, but I'm gonna guess it's R. It's not. It's T. Oh well. That means the next one is R. I hope. Yeah. So this one, we're solving for, well, let's see here. If $4,000 is invested at 4% compounded annually, how long will it take to accumulate to $6,000? So, how long will it take? That sounds like T to me. Solve for T. We'll jot down all the information that we're given. It looks like P is 4,000. P is 4,000. R is 0.04. Compounded annually, so N is 1. That's cute. And it's going to accumulate to 6,000. Same formula, right? We're just kind of working and massaging this formula. Bless you. 1 plus R over N times T. Sneaky. Well, let's see. Let's plug in chug and see what happens. 6,000 is 4,000 times 1 plus 0.04 divided by 1 to the power of 1 times T. We can still simplify inside the brackets, but you can see the problem is that the T is in the exponent. Right? Now, you might remember something about how do I bring exponents downstairs? How do you bring exponents downstairs? Could use logs, right? It's probably our best bet. And how about this? If you're not comfortable with logs because we haven't covered them, and I'm not sure there's any, I didn't make any time in the schedule. Well, that's a bummer because I really like exponents and logs. But would have been nice to have it now, I guess. But how about this? I'll give you the worked out formula so that you don't actually need to know about logs if you need it on the test. So what would it look like? We can simplify this as 6,000 is 4,000 times 1.04 to the power of T. To solve for T in the exponent, orange maybe. To solve for t in the exponent, first isolate the exponent. I'll just do exp, which looks like this. 6,000 divided by 4,000 is 1.04 to the power of t. Now I've isolated that thing. 6,000 divided by 4,000 hopefully simplifies to something nice, and it does. Simplifies to 1.5 is 1.04 to the power of t. Let me add a page here. So now we're just stuck with something to the power of t. So now take the log, and if you've worked with logs before, which I kind of assume to some extent, right? You know there are logs of many bases, and it actually doesn't matter which base you use. So I like to use base e, the natural log. Okay? But what does that look like? Take the log of both sides. We can use log base 10, which is just written as log. It's the common log. There are all these different logs, but the log of 1.5. Now what the log does is it just stays a number. Okay, and so it's a button on your calculator, and we'll try to find it. But for now, let's just write out what we need to do. Take the log of both sides, the log of 1.04 to the power of t. Now the beauty of logs, okay, and really the only thing you need to know about a log is the log of a to the power of x is the same as x times the log of a, which means that this little guy, this x, kind of can get sent down in front. And now all of a sudden, he's a free agent and you can solve for it, right? Because the log of a number is just a number. My grandpa, when I was going to grad school, and or maybe it was in my undergrad, because I did my undergrad in math. And he said, like logarithms and such. Aha. Because logs used to be really difficult, right? And so it was a complicated mathematical procedure, but now we just have a button. And so I didn't really get it. I'm like, yeah, we use logs all the time, but like, who cares? And so, like logs and such. Yes. Aha. He was right, but yeah, we did other things. You know? And so now, what this means is this t, the reason we took the log is so that we can send that t out front, and they're equivalent, right? So now we have the log of 1.5 is t times the log of 1.04. Huh? This is a number, and this is a number. We're going to find what those numbers are, but just to emphasize that they're just numbers. So let's take the log of 1.5. On your calculator, depending on kind of the type of calculator you have. You should have a log button. And so mine is fancy and it wants what base. Let's use base 10. Most calculators don't have that, but this is an engineering one, so they know what the people want. I get log base 10 of 1.5 is 0.17609125591. I'm going to store that just so I don't have to repeat that. And your calculator probably has a store function. And now's the time to explore it, figure out how it works. And so the log base 10 of 1.04 is 0.0170333 1, 2, 3, 4, 393. Keeps going. Which means that T is 0.17609125591 divided by 0.01703333393. Or it might be simpler to say the log of 1.5 over the log of 1.04. But if you were kind of quick to get rid of those logs, right, that's fine. Which I get recall A divided by that. I get a T of 10.338033507 years. And you don't need to convert the 0.338 into months or anything like that, right? How would you do it if you had to? I'm going to isolate -10, so I just have the decimal. And then there are 12 months in a year, 4.06. Right, so 4 months in roughly a third. Makes sense. But I don't expect that. I'll just leave it as a decimal. In fact, if I'm marking, I'll just be looking for the decimal and then I'll stop when I see something that makes me happy. I'll move on. We can use logs of other bases. Such as log base E, which is, let's say of X, which is the ln of X. You probably have an ln button, right? So this is the natural log. What happens, right, if we jump up here, T was the log of 1.5 over the log base 10 of 1.04. So what if we replace those log base 10s with log base E, right? And so now T could be, oh, I do my, in statistics, the only log we use is the natural log. So my ln is this kind of sloppy script. And I call it a log. I know, everyone hates that. ln, lawn, some people Oh, 1.5, not 1.05. I would have gotten a different answer. Wouldn't that have been confusing? There. So let's try that. You have a log button, you have an ln button. That's just the way it goes. And most scientific calculators do have log buttons. The natural log of 1.5 divided by the natural log of 1.04. Well. 10.3380357, which is the same. So it doesn't matter which base you use. So that's kind of cool. Does anyone have one of those buttons where you can determine the base? Maybe? No? Straight logs? Logs and lawns? No. Logs and logs. I think, now I'll say this, but we're a ways out from test 2. But I think this is a reasonable bonus question and not something I would expect you to do because we didn't spend any time on logs. Besides this little blip, but kind of fun. Oops. Any questions before we do this next one? If $5,000 is invested now for 6 years, what interest rate compounded quarterly is needed to obtain an accumulated value of $8,000? Yeah, did a comma here, but not here. Solving for what interest rate? Solving for R. Okay, so again, just kind of talk ourselves through this statement here. The principal amount invested is 5,000. T is 6 years. Compounded quarterly, which means 4 times per year. And we want an accumulated value of 8,000. Okay. Same thing. A is P times 1 plus R over N to the power of N times T. We're going to plug in all our values and then see where that leaves us. I've got 8,000 is equal to 5,000 times 1 plus R. That's the one I'm solving for. Over N to the power of, N is 4. 4 times 6, still 24. And simplify this a smidge, not much, but a smidge. Let's start with that power. 1 plus R over 4 to the power of 24. Just as we did with isolating the exponent, we're going to need to isolate this thing that's to the power of 24, right? How do you undo a power? We use the root, right? The 24th root in this case, right? And so here, but first we need to divide both sides by 5,000. So we need 8,000 divided by 5,000 Does that make something nice? I hope. Whew, it does. 1.6. I'll jot that down before I lose it. 1 plus r over 4 to the power of 24. And I'll write that out again. So now, right, to get into the inside of the exponent, to remove the exponent, we take the 24th root of both sides. If there's an equal sign, as long as you're doing it to both sides, you can do whatever you want. How do we take the 24th root? Looks like this. The 24th root in the crook of 1.6. 1 plus r over 4. Should I do what technically happened to the 24th root or the 24th power? We haven't worked a ton or hardly any with these powers. 24th root. So I do want it of the 24th. But the 24th root, you can use it as, or rewrite it as to the power of 1 over 24. And that's how you're going to take any root of any number. And what color did I use for there? Pink. Means it's important. So note the nth root of a is the same as a to the 1 over n, just generically. Which means that the 24th root of 1.6 is 1.6 to the power of 1 over 24. So this is 1.6 to the power of 1 over 24, which is 1 plus r over 4 to the 24 to the power of 1 over 24. Now what happens with these exponents is they're multiplying. And so this becomes 24 over 24, which is a power of 1, and that's how it disappears. Right? So now, any calculator can do 1.6 to the power of 1 over 24. Just make sure that you keep your 1 over 24 in the exponent, right? So you want to use brackets maybe. Brackets. 1.6 to the 1 over 24 is 1 plus r over 4. We're so close to unearthing that r. So the next thing we have to do, we have to subtract 1 from both sides. Right? Should we simplify 1.6 to the power of 1 over 24? Let's see. Fine. 1.019776499. That might be nice to check your work. 1 plus r over 4 1.019776499 minus 1 is r over 4. Bless you. Multiply both sides by 4. So r is 4 times 0.019776499. Point 07910599556 or 7.91%. Compounded quarterly, right? Every quarter you only get a quarter of 7.91%, right? But that's what it's going to take to have what grow to what? 5,000 grow to 8,000 in 6 years. Nice. Mark. Step away from the plate. And now we've solved for all the things. All the things. Like I said, n will be given. So we don't need to solve for it. I didn't know this was the case, but I guess banks are required, and maybe it's just in the States, but I think it's true here too. Banks are required to state their interest rate in terms of effective yield or effective interest rate, okay? And that makes them comparable, right? And so for comparison purposes, the effective rate is also called the annual percentage yield or the annual percentage rate. And this is probably the one that we see most frequently, I would say, the APR. And so the effective rate is the interest rate compounded annually. That would, they're missing a word here, but that would be equivalent to the stated rate and the compounding periods, right? So it's just a way of bringing all these rates, right, to an equivalent kind of comparable rate that's compounded annually. And so I want to just give it to you. If a bank pays an interest rate R per year, compounded N times per year, that's all the same, then the effective interest rate is given by, and we use a little R with a subscript EFF, or kind of, you can write out effective if you want, but just to indicate that it's the effective interest rate. And remember, the effective interest rate, by definition, is the annually compounded rate. So if it's being compounded N times per year, the effective interest rate is going to be giving you the same yield, but compounded annually instead, right? Everything is familiar at this point. 1 plus R. R is the rate, the original rate, right? The kind of actual rate per year. And then compounded n times per year, it's to the power of n. Right? Same values, and then minus 1. Yeah. So if Bank A pays 7.2% interest compounded monthly, what's the effective interest rate? Let's see here. We want to find the effective interest rate. We don't need a lot of components, right, to find the effective interest rate. We just need the rate and the number of compoundings. Part A, we have R is 0.072 compounded monthly, so n is 12. And we want to find the effective rate, which from above here is 1 plus R over n to the power of n and then minus 1. You'll see why you have to do minus 1. It's because otherwise your rate would be 100 and some odd % per year, which is juicy, but I don't think they can do that. 1 plus 0.072 divided by 12 to the power of 12 minus 1. Take it nice and slow, 0.072 divided by 12. Then add that to 1. Then take it to the power of 12. Oh, you know what? It's our first one, so I should write out the steps, I guess. .072 divided by 12. Take it way back, 0.006 to the power of 12 minus 1. X to the power of 12, I get 1.074424168, but don't forget to subtract 1. 0.07442416772. What does this mean? This means that 7.2% compounded monthly is going to give you the exact same result as 7.44% compounded annually. So here, let's jot that down. This means 7.2% compounded monthly. I think it was monthly, yeah. Will yield the same results as 7.44% compounded annually. Knowing that, if Bank B pays 7.25% compounded semi-annually, what's the effective interest rate? If we're able to bring them both to the effective interest rate, then we can compare the two, right? And so face value, I would say 7.25 is better, right? That's a higher interest rate, but it's compounding semi-annually instead of monthly, and so that's probably going to impact it. And so to be able to compare them, Now, let's do bank B, 7.25% compounded semi-annually. Again, what's the effective interest rate? Oh. Good enough. R is 0.07, I think 25. And N is 2. The effective interest rate, what's the formula? 1 plus R over N to the power of N minus 1. One plus 0.0725 over 2 to the power of 2 minus 1. This one I'll do like I normally would, to the power of 2 minus 1. Just skip straight to the good stuff. 0.0738140625. So now, this means that, you copy this. (7.25% compounded semi-annually will yield the same results as 7.38% compounded annually. If I'm comparing 7.38 to 7.44, I think I like 7.44 better. Right? And so I would choose bank A, since 7.44% is higher than 7.38%. Nice. That's kind of handy. Want to know something mind-boggling? There's such a thing as continuous compounding. And it's just always compounding. Not even every second, it's always compounding. And that sounds good, right? But it also means that your interest rate is essentially being sliced on a continuous scale. And so it's just being portioned out, right? And so what happens with continuous compounding, it is going to be very similar. In fact, it's very similar to all the other compounding frequencies. It's just that the formula changes just slightly. Okay? And so if we have continuously compounded interest, then we get a new formula. It's not that common to have continuously compounded interest. And so it's not one that I want to focus on, but it is kind of a fun thought experiment, right? It's compounding, not even just every second, but continuously compounding. And so it behaves slightly differently, but the formula is this. An amount P is invested for T years at an interest rate of R per year, same as always, right? Compounded continuously, then the future value, or A, the accumulated amount, is P times E, so that special constant E, to the power of R times T. Yeah. I jump in and give you the effective interest rate right away. So if a bank pays an interest rate R per year, compounded N times per year, then the effective interest rate, that's wrong, R compounded continuously, then the effective interest rate is going to be e to the r minus 1. So let's see here. I'm trying to decide how much we care about continuous compounding. Not a lot. We only have 3 examples on it. So. Cut it out. No, let's try it. It's pretty fun. I think the formula is a little bit simpler. Key here is compounded continuously. $3,500 is invested at 9% compounded continuously. Find the future value, which is your accumulated amount, A, in 4 years. So same as always, I think it's nice to highlight what it is you're looking for. And we are given P is 3,500. R is 0.09. And T, can I squeeze it in on the same page here? Let's try, is 4 years. And we want to find A is P to the E, or times E to the R times T. Okay, fine, I can't keep it. Maybe I can. Not quite. A is 3,500 times E, which is a button on your calculator, I'm sure of it. It's a constant, just like pi. Usually they kind of hang out together. So you'll want to find an E on your calculator. Usually it says E to the X, right? So let's see here. Mine is above my natural log button because they're buddies. Let's see here, 0.09 times 4. So on your calculator, you probably have an E to the X button. Probably. I didn't want to say it, but I do too. I have a just straight E or E to the X. Let's see. So E to the 0.36, let's start there. E to the 0.36, I'm gonna jot down what I get here so you can compare. 3,500 times 1.43329415. Then I can multiply it by 3,500, and my accumulated amount is 5,116.75. 0.652951 or 5,016.65 pennies. What if it was just, instead of compounded continuously, how much would you have accumulated if it was compounding something slow, like annually? Right? So let's see. Find A if compounding annually instead. A is P times 1 plus R over N to the power of N times T. So I'm compounding annually, and I want to solve for A. Let's see here. My P was 3,500 times 1 plus my rate is 0.09 divided by 1 times 4 years. I get 1.09 to the power of 4 times 3,500, 4,940.535635, or 4,940 and 54 pennies. Compared to 5,016 and 65 pennies if I was compounding continuously. Right? So these are kind of your two extremes, right? But there's not that big of a gap between these two, right? It's big. I think I prefer the 5,016 if I had a choice, but not that as big as you would expect when you think about compounding continuously. If an amount is invested at 7% compounded continuously, what's the effective interest rate? So from this continuously, then we have the special formula, which I'm gonna snag here. I want to find the effective interest rate, and R is 0.07, which is the only component that we need. So the effective interest rate is e to the 0.07 and then minus 1. We just found that e button, e to the 0.07 minus 1. I get an effective interest rate of 0.0725081825, or roughly 7.25%. Which isn't that different from 7% compounded continuously, right? They're different, sure, but going back here just briefly, this is the interest rate that I would need in this formula here, right? Compounded annually in order for the A to become 5,016 and 65 pennies, right? It's our last example. And then we can have a race for your homework problems again. If an amount is invested at 7% compounded continuously, how long will it take to double? Kind of a thinker. Okay. First, let's pick out what we know. It's compounded continuously, which tells me which formula to use. Now, I want to figure out how long it'll take to double, which means I want to find some accumulated amount. And so the formula that I'll need is this guy. PERT. Oy. Yeah. R is 0.07. Okay. We're trying to find some t. How long will it take? Okay. We were told R is 0.07. But I still need A and P. We've got a couple of options. You could pick a value for P and then let A be 2 times that. Right? Reasonable. Or you could even say A just has to be 2 times P. Right? And so I'm going to let just P be P and A can be 2P. Snazzy. But you're just as well off if you say I'm going to let P be $100 and then A, if I want to double it, should be $200, right? The result is going to be the same. So now in this formula, I can replace it with 2P has to be P times e to the 0.07t. I want to get at that t in the exponent, which means I need to isolate e to the 0.07t. So I need to divide both sides by p. Right? And so I get 2p over p is e to the 0.07t. But p over p is just going to be 1. Right? And so I'm left with 2. E to the power of 0.07 times t. To get at that t in the power, I'm going to use the log, right? You take the log of both sides, and that's going to let you bring that 0.07t up front. I'm going to use the natural log, just because it is base e, and that'll cancel. So I'm going to take the log of 2 is the log of the natural log of 0.07 times t, which is the same as the natural log of 2 is 0.07t times the natural log of e. You can try it on your calculator, but the natural log of e to the power of 1 makes it just e is 1. So that's nice. So then I'm left with t must be the natural log of 2 divided by 0.07. The natural log of 2, is 0.0693, and divided by 0.07, I get a t of 9.902102579 years. So it's going to take 9.9 or almost 10 years for any investment to double, right? At a rate of 7% compounded continuously. We could have done this for the compound frequency or the compound interest that we were talking about earlier, but this one's a little bit cleaner. In fact, there's a rule of 72, usually we call it, or the rule of 70, which says that, let's see here, the number of years to double money is roughly 70 divided by the interest rate as a percentage. So here, this is as a percentage. Technically, it's the natural log of 2 divided by the rate as a decimal, but that's just not as catchy, right? And so if you take 70 divided by the interest rate, just gives you a quick approximation for how long it would take any money to double, right? $1 to go to $2, $1 million to go to $2 million. It just depends on what you have, right? And so let's see here. I think a kind of a common interest rate right now is, well, there's some nice offers of 5%, but they only do those for like 3 months or 6 months or something, and then it drops down to, I think, what is it, 2%, something like that. So at 2%, now it actually doesn't matter how often you're compounding, because it all comes out in the wash. It's just an approximation. And so at 2%, how long will it take for $1 to double? Well, the rule of 72 said, or 70, they use 70, that's fine, is 70 divided by 2. It's going to take 35 years to double. That's fine. If you're going from $1 million to $2 million, $1 to $2, but on the flip side, you're not going to need that dollar. You can let it sit there. And then 35 years later, cha-ching. Wow. But it does give you a nice kind of tool to determine if you like a rate or not, right? How long you can determine if you're comfortable with that doubling time, whether you want it to double or whatever. It just gives you kind of a guideline of how long is this going to take, right? A small lifetime is how long it's going to take. Okay. We'll call it there. If you want to work on the homework questions, I saw that the links were broken last day, but then I checked yesterday and they were working again. So hopefully they're still working. But, oh, that's what I meant to say. I did have some admin. Sorry, guys. It's just that I posted the PDF of the textbook sections that we're using at the top of our Moodle page in general resources. It's down here. I only did the sections that we covered in class. And with that, I release you. Have a great weekend. I'll see you on Tuesday.